the philosophy of design, then how to design beams, columns, tension members, plate girders, beams, columns, and all those things itself. Now we will come to our almost last topic, as far as this course is concerned, that is this plastic analysis. Okay, so this is what the last topic. So last year, what happened was, because of Corona, some classes we missed. I mean, of course, I missed some classes. The students also some issues was there. So this topic was left. Okay, so we were unable to cover this topic. But this year, I think we are going. Everything is on time. So this thought, you see, we can close this topic itself. Okay. So now the first thing is, why do we require this plastic analysis? Okay. So like now, whatever you have studied until now is all about design. So you have seen how to design, these beams and other things also. So in the entire course, now we will be looking at, the analysis actually, how to do this analysis in plastic region. So this is what, we are going to discuss. Okay. So this is a very, the important topic in steel structures. Maybe RCC, not this one, but in steel structures, say. So this becomes a very important topic itself. So why do we require this plastic analysis? Okay. So now if you see, the answer is in this stress strain curve. So this is our stress strain curve for mild steel and of course high strength steel. So anyway, our construction, we are going to use this mild steel, so the entire core. So this is our stress strain curve. Okay. So now you can see here clearly that, so this portion, say, so this initial, the portion, this is what we call as elastic region. Then this entire portion, say from here to here, this is what we call as plastic, the region. And you can give variety of names, so this is elastic. So this is what we call as, constrained plastic flow, unrestricted plastic flow. Then this is a plastic flow actually. Okay, so this entire region we call this as a plastic flow. Now, when you look at this stress strain curve, say, okay, so now the most important thing what happens is, if you see the yield strength, that is f of y is somewhere, here in this region itself. And then, and if you see, and if you go into the plastic region and you test the specimen until collapse, say, you will get this maximum, the collapse load, that is Fu, you will get this one. Now, if you see your ratio of Fy to Fu, say, so now this portion, for steel, the main advantage is, so it has a lot of strength in the plastic region also. Or sometimes, we call this as reserve strength also we have here. So there is a huge, like, you may have see, 50%, 35%, the huge difference in strength is there. Now, elastic analysis says, so now when you read elastic analysis, whatever you have studied in your structure analysis courses, the bending moment diagram, shear force diagram, whatever you have done. So the main assumption is you are in this range only. That is this elastic portion itself. Okay. So now, but because steel has extra additional strength, say, okay, so this strength also can be utilized in our design and analysis also, and then you can make more economical, kind of sections basically. So that is the idea. Okay. So because this ultimate collapse load and Fy, say, there is a huge difference is there, like 30 to 50% more or whatever. So why don't we use this also in our design, so that you can make it more economical. So this is the main objective of this plastic analysis. Okay. So anyway, so now here, so this is what we say. So now I hope all of you know, because I shared you in, I think, the starting slides where I examined, the metal property of steel and have explained you this stress strain curve here. So this is what constrained plastic flow, this region, unrestricted, plastic flow. And what do you call this region? So any of you can tell me, what do you call this region, this portion essentially? See, once you have loaded the specimen, say, it goes into this, the constant whatever here. Then after that, once again, the load carrying capacity increases. Okay. So what do you call this one? This region, say. Now, see, what do you call this one in our steel design? Long back, I have explained you, right? What do you call this region? No.
Sir, strain hardening.
Excellent. Okay, this is what we call as strain hardening. Okay, so this this portion is this one. Okay, so the strain hardening also we call. But generally, plastic means everything is plastic only. Starting from once you class elastic, say you have all plastic only. But of course, we give several names itself. Okay. So for steel, so there is a huge difference between Fu and Fy. So we are trying to cache it actually, this Fu itself, such that you can go into more economical designs. Okay. And then what do you call this one, like this portion, say, like you can say this ultimate strain or whatever. and here's your yield strain, says epsilon y. The ratio of this to this, what do you call? The ultimate strain to this portion, say the elastic, this portion, what do you call this one? What do we call in stress strain curve? The ratio of this ultimate, this final one versus this, the elastic, this one, say that we call as the ultimate deformation to elastic deformation. So we call that as. You can read this one. So what is this? This ratio we call this as. See, what is this one? So what is that I have written here? So this is known as. See, all of you are there.
Yes, sir. It's ductility.
Ductility. Okay. So anyway, fine. So this is what we call as a ductility, and the main advantage for steel is, steel is extremely ductile actually. Okay, so it has a huge ductility. So this is what we want to cache it in our plastic analysis. Okay. So now anyway, the elastic analysis, all of you have done courses. CE 2020 structure analysis courses. You have done how to draw. Like if you're given a beam or a frame, say, okay, so how to draw, the bending one diagram, all those things you have drawn. Okay, so something like this, bending moment, shear force, and all those things you have studied in your mechanics of materials and then structure analysis courses. Okay, but the most important thing what you have done in those courses is that is all elastic analysis only. So now what is the fundamental equation you have used to solve to get the deflection? So like a simply supported beam is there, say UDL or whatever this one. If I want to find out a deflection delta, okay, so what equation you have used? What is the main differential equation? The governing differential equation for beams. Now, what is that famous equation, right? Everybody you used, right, to so get the displacement. Say. So what is that you write? No, M is equal to bending moment is equal to what is that expression? Any of you remember? What is it? How do we get deflection? M is equal to
EI
uh,
T T square W by Tx square.
d square y by dx square. So this equation comes from your simple bending formula. You remember plane sections remain plane, linear and all other things, linear, elastic and others. This is an assumption basically. So you do linear elastic assumption. So you get this differential equation. So you solve it, you get the deflection. You draw the bending one diagram, shear force diagrams and all those things itself. Okay. So whatever you have studied in your courses, CE 2020 or CE 2310, that's mechanics of materials. Mostly, we assume that all the structures are in this, the elastic zone only. We have not even crossed into this one. Okay. So this portion only you are there. Your whole analysis here, this one itself. Okay. And of course, generally, the working stress method are generally in the design also. We say that, anywhere in the structure, say, when you are applying the load, so at any point in the structure, the entire structure, nowhere the stresses will be always less than, the yield stress itself. So this is also, what we have studied basically. So that is how, this analysis comes into picture itself. But now the problem with steel structures is, because it has a huge ductility and it has a huge plastic strength. So much of strength is reserved strength is there in the plastic region. So this analysis, may become, more conservative or it may be uneconomical, kind of thing itself. Okay. So and another major flaw with this elastic thing is, suppose if this is a simply supported beam, this is our bending one diagram, say, okay. And of course, if this rectangular cross section, all the bending stress distribution you see is something, like this top one will be compression, bottom one will be top one will be in tension, top one will be in compression, bottom one will be in tension. So this stress diagram itself. So now what happens as you keep on increasing the load, say, So the points which will reach the first, the yield stress is only the top fiber and the bottom fiber only. And then if it is a simply supported beam, say, so the bending moment is maximum only at the center point, that is a PL by 4. So when you keep on increasing the load, say, what happens is in the entire beam, say, only 2 points basically in this cross section will get the sigma y itself. So your elastic analysis, so but what happens is, this entire section here you are having, this region itself is still elastic itself. So it has a lot of reserve strength and others, this happens like these our yield points. So it has a huge reserve strength, that is ultimate strength or whatever. So, so this results into uneconomical kind of things with, the conventional, the elastic, the analysis itself. So that's why you see the plastic analysis we try to see. So the plastic analysis is essentially, same. We will draw the bending moment diagram. We will do all the same to same whatever you have studied previously, but we will see how the structures behaves beyond the elastic region actual. So this is like an extension of your elastic analysis itself. And of course, the stresses in the structures, this exceeds the yield stress of the material. So this is our, the sigma can be greater than sigma y. So that sigma y concept, we will remove from our analysis, and then we proceed and we draw the bending moment. We will find out how the structure is going to collapse, say, in the plastic region itself. And then the main and how we will use it in design is like this. So now we will calculate the load which causes complete collapse. That means in the structure complete, that the ultimate load or whatever we will try to find out, and then we will make sure, say, that this load exceeds the largest applied load. So like, we'll find out a factor of safety, and then we will say that your design load will be whatever load you have, say, you divide by some factor of safety or whatever. So we will find out safety factors, say, from this expression, and then you do the design analysis also. And of course, as already I told you, this plastic analysis is very popular or routinely used in steel structures. The reason is, the structure can take more deformation, that is, the ductility is more. So that is why this plastic analysis becomes very important, and then very advantageous for steel structures. And of course, it results in more the economical structures, okay, because you are allowing the structure to go beyond the elastic region. So obviously, the design loads comes, and then your structure will have economy, because the size of the sections, the size of the dimensions, they will become small. So obviously, you will the weight of the structure will come down, and then it leads to economical thing itself. Okay, that is the main advantage. So this is how. Now, so if you do this, if you look at a cross section, say the same simply supported beam, okay, subjected to concentrated load or whatever, and then you find out the stresses here. That is this portion, say, that is a maximum bending moment portion here. This is how the strain distribution and the stress distribution over that cross section. Okay, so if epsilon is less than epsilon y, say, so your structure is still f less than fy, it is still in the elastic analysis. Okay, so this is what you have studied in your for the mechanics of materials, and then this is the structure analysis course. Now when epsilon becomes epsilon y, or f is equal to fy, say, that is the load has been slightly increased. So what happens is the top fiber, say, the top and bottom fiber, they will reach the fy, that is the yield is this one will come. Now as you keep on increasing the load, say, so you can identify these points in this graph also. So this corresponds to you are maybe you are located in this elastic region itself. Now when f is epsilon fy, say, so this one corresponds to this point in the graph, that is a point B or whatever you can say. Now as the load is increasing, say, strain also increases, stress also increases, and this slightly the plastification starts actually from the top one to the bottom. But still this portion is in elastic region, but this is gone into plastic region. So this may be somewhere in between, you see, B to C itself. And then when n epsilon is equal to epsilon s, that is this portion here. So this the distribution, the stress distribution comes to here. And then when epsilon is greater than epsilon x, say, slowly the strain hardening comes, and then this whatever plastification has happened, say, still it can carry some more load, and then you see it goes like this, and this is how and finally the plastic hinge forms, and then the structure gets collapsed. So this is what exactly happens. If you try to see the mark this this entire this one here, and if you try to see looking at the stress strain curve and looking at the stresses in your cross section, say, so this is exactly what happens in reality. Okay. Well, and of course, if you want to test, you can easily test it in the lab. So this is a portal frame, say, steel portal frame, subjected to a concentrated load on the top. Okay, so it is a fixed the portal frame. Okay, so this is how the load has been applied on the portal frame, and the load has been keep on increasing, to reach the ultimate collapse. So finally, in the collapse side, so this type of, the hinge or whatever, you will see in practice. Okay. Now this also, suppose if it is at the fixed end, say, okay, the bending moments will be very high, and here automatically, there's a hinge forms, and then this is how, a steel structure collapses actually once it goes into, if you test the structure, say, until the collapse, so these type of things happens, and curvature keeps on increasing, it cannot take more load, and then finally it collapses. Okay. So now anyway, so in our plastic analysis, so this is the exact thing what happens in reality. So that if you use the entire stress strain curves until strain hardening and then collapse, is how, you will see the cross sections, how the stresses and other things increase over the cross sections. But now what happens is, if you want to model this entire stress strain curve, say, the problem here is, from here it may be linear, then it may be constant, then it will go to non-linear range itself. Okay. So here the problem is, you can model the entire stress strain and you can find out ultimate collapse. But the problem is, it becomes complex because of the non-linearity, and then, you have to do so many numerical, the approaches for this. So what we try to do is, we will not go into all those things. We will do some assumptions and make a simplified procedure to find out the ultimate load. Okay. So that's what we said. So the plastic analysis. So we use this. We will make use of the reserve strength basically. Okay, beyond the elastic state of the structure. So the structure's reserve strength, we are calling this one. So which allows, the structural members to be loaded without failure. When their maximum bending capacity is reached, is utilized in the elastic plastic state when the loading is increasing. So that's what, this plastic analysis is all about. And obviously, the design becomes more economical because the dimensions automatically they get reduced, and you can save money itself. Okay. And of course, you see, and the plastic design, say, it is essentially what happens is, the movement redistribution basically. So at one place, the hinge gets formed, or one get collapsed, say. Suppose if it's indeterminate structure, the thing bending moment diagram, they get redistributed here, and then it still tries to carry the load itself. So the plastic design is something like, you can say movement distribution, the movement redistribution, you see, of our steel structures. Okay, this is essentially, we will see after this one. And because, as already I told you, this portion, say, where this concept, this portion, okay, because of the non-linearity, so to do analysis, it becomes complex, because non-linearity handling is very difficult, and it is in the strain curve, and you cannot solve, your equations are not valid, and you cannot have any closed form solution. You may have to do only numerical approaches. So this is slightly complicated. So what we do is, in our plastic analysis, in our engineering, we don't do complicated analysis. We do simple assumptions and simple formulas. We keep the design as simple as we can. So, like for example, in our simple beam theory, say that, plane sections remain plane, we make so many assumptions, and then, we derive a simple formula that, m by I, E by Y, you followed, right? So this simple sigma by Y is equal to E by R. So we derive this simple kind of thing. So in plastic analysis also, we try to do this type of simplification. So for this, we ignore this strain hardening portion itself. Okay, so this is a main assumption in our plastic analysis. Okay, so that means, we will go, the stress strain curve is not like this. The stress strain curve is something like this. Okay? So this is what we try to do this one. So if we ignore the strain hardening set, so whatever plastic analysis we try to do, the theoretical plastic, whatever you do from our analysis, whatever load you are going to get is always less than the true load basically. And of course, the resulting design is, will be always, the conservative itself. Okay? So this is what we try to do itself. Okay? So anyway, so this is what we said. So the main assumption of plastic analysis is, so this is the one main assumption is, the parts of a structure, say, that has been stressed to the yield point, it cannot resist the additional stresses. This is the first most important assumption. So like for example here, this portion, say, the stress distribution is like this. Okay, so let me draw here itself. So if I see the cross section, yeah. So this portion of the beam, say, so this portion has become plastified actually. So our assumption is, so this portion, say, once it has reached yield strength, so this will not carry any load itself. Okay, so the additional things will be resisted by the elastic region itself. Or if you take the simply supported beam, or a fixed beam, or whatever, say, or whatever, so suppose, or propped cantilever or whatever. So let us say you have a concentrated load, say. So the bending moment where it will be maximum will be at the fixed support. Okay. and then if the other maximum bending moment will be below the load itself. So what happens is, as you keep on increasing the load, say, so this portion, the bending moment will reach almost, your yield strength, M plastic stage, and hinge forms. So once the hinge forms here, say, it will not take any more load itself. But since it is indeterminate structure, say, so this becomes, a simply supported beam itself, and the extra load, say, that will be carried by the remaining portion of the beam itself. Okay, so the once it has been plastified, once a hinge has been formed, it will not carry any more load. The remaining portion will take care about the additional load itself. So this is one most, the important assumption we try to do in our plastic analysis, and that's what we said. So any additional loads, say, or stresses will be transferred to other parts of the structure where the stresses are below the yield stress and thus in the elastic range and able to resist the increased stresses. So these are most important assumption we try to do in our plastic analysis. Then other most important assumption is, anyway, just now I pointed out the strain hardening we are ignoring. Okay, so the stress strain curve is, just like this. Okay, it's a bilinear, this type of a curve, we assume this portion, say, the strain hardening and other things we ignore, because you can include that also, but you have to do numerically. You will not be able to do some simple formulas, or simple design cannot be done if you include this portion also. So this also, we ignore actually. So that means, you are still in the safe side. Okay, so this is the advantage. So our assumption is like this. So the stress strain curve is just like this, and then, so we go only up to epsilon greater than epsilon y, and we are not going to take about the strain hardening. The strain hardening, say, so you will get extra strength also. Okay, so this we are ignoring. So our assumption is, so when F is equal to Fy, this happens, and when, as you keep on increasing the load, so the whole load basically, okay, the plastification, it keeps on coming down, and finally, you will see this type of a distribution. So this we call this as, the plastic hinge formation. No more, things, no more load it cannot take. So this is what we try to do itself. Okay, and then and the steel we are doing, this is what we call as elastic, perfectly plastic material. So these are stress strain curve actually. Okay, so this type of stress strain curves, we call this as, elastic, perfectly plastic material itself. And then this movements at which, everything becomes plastified, we call this as a plastic movement. Okay, so we define this as a movement, say, that produces full plasticity in all the member cross section, and of course it creates this plastic hinge. Okay, and of course, in when we discussed about beams, I have already introduced you to all these terms itself. We defined what we call as, the shape factor. Okay, I hope all of you remember plastic movement to elastic movement. So this ratio we call this as a shape factor. Any one of you remember what is the shape factor for our I sections? So the shape factor is given in our steel tables also. You remember when we discussed beams, I have told you also. So what is the shape factor for I sections typically? Any of you remember? Or for rectangular cross sections, so what's the shape factor?
So 1.5.
Yeah, 1.5. Very good. Okay, so it is 1 for I sections. Say I section
1.12, sir.
1 point.
1.2.
Yeah, 1.1. It is available in your steel tables. Okay, so the shape factor is also something like, your reserve strength or whatever things are, available in your for to carry out a plastic analysis. So this already we have discussed. Okay, so what I am trying to say is, so your original stress strain curve of steel is something like this. Okay, so this we are ignoring. So this we are approximating this as, something like this. Okay, so this we call as elastic, perfectly plastic material to do our elastic plastic analysis. You can do, you can include this portion also, but you may have to do numerically. You cannot do analytically, or you will not be able to get some simple formulas or something which you can use it in design. So these are the assumptions. So two assumptions. One is, once a structure has been stressed to the yield point, say, then it cannot take any additional stresses, and any additional stresses you have to transfer it to other portions of the cross section or even other portions of the beam where stresses are below the yield level. So these are the main fundamental assumptions. Okay, so this elastic, so this what, anyway, the same thing, the whatever stress strain curve, say, since if you are talking about the beams, so it is easy you followed. So to the same thing, you can translate it to movement versus curvature itself. Okay, so these are elastic region is here. So the AB, say, so this is your elastic region. So you call this as a yield movement, and then, the curvature or whatever you have here. And then as you keep on increasing the load, say, generally, it goes like this, and then it becomes like this. So this we call this as a plastic movement. Actually, same stress strain curve only we are writing in terms of movement versus curvature for a cross section. Okay, but in general it will be non-linearity also will be there when it goes from elastic to plastic. Also you will see this type of curved also. But what we try to do is we ignore this non-linearity. We just approximate this as a straight lines. Okay, so that our analysis becomes very simple basically. Okay, and of course the shape factor you can write in terms of section modulus or whatever we said. But anyway, because you can also write as a ratio of MP versus My itself. Okay, this also we ignore the non-linearity. So this already, we have discussed in our beams class. Okay, I already showed you these slides and how to compute the yield movement. The My. When for this case, how to find out. We have already seen, like you can take the lever arm and you can multiply. Those things already. So My for rectangular cross section say is BH square by 6 you get. Then if it is in this type of region, say some portion is plastic, some portion is elastic plastic stage also you have already given this thing how to calculate, and this is how it comes also. Then finally fully plastified sand we get, I think, BH square by 4 itself, and that's what the shape factor, as you rightly pointed out, it turns out to be 1.5 actual. Okay, so you know how to calculate all these things. We're not going to those details. Okay, and now this is what it looks moment versus curvature. Say for the I sections is ideal is 1, then I section is 1.14, and then for this type of things it is a 2 basically. It's almost the double kind of thing. And for rectangular cross sections it is 1.5, circular it is 1.7, hollow 1.27. So these are all these things are anyway available in our steel tables. You can easily analytically also you can calculate itself. Okay, so anyway, so now in our plastic analysis, already I told you the assumptions, I have told you all those things. So the main concept is based on this plastic hinge. Okay, so where this plastic hinge gets formed, then finally the plastic collapse of the structure, how the structure will collapse basically. Okay, and because collapse means not just as a, it would be the statical indeterminate structure. Say one plastic hinge may not be sufficient. You may have to have multiple plastic hinges also. So that's what we call this as a mechanism actually. Okay. So mechanism means the failure of structure only. So what type of mechanisms it is going to follow to come to failure itself. And then we will be calculating elastic plastic movements. The same bending on diagram. Elastic this one plastic bending on diagram. And then finally, we will be talking about shape factor. The load factor, and then collapse load and other things also. So this is what essentially we try to do in plastic analysis. It's very simple. Just you should understand plastic hinge and how the structure is going to collapse, what type of mechanism it is, how many plastic hinges are required to collapse the structure, and what type of mechanisms, whether it's a beam or a frame or what type of mechanism that is going to collapse. Then once you decide the mechanisms, we will find out elastic plastic movements depending on diagrams we will plot. And then finally say the shape factor, load factor, collapse load, and all those things we will find out in our plastic analysis. So this is what exactly we do. So this is a simple, the simply supported beams subjected to concentrated load at the center. Okay. So all of the bending moment diagram. So what's the where will be the maximum bending moment, and what is its value? So the concentrated load is PC, and L is the length of this beam. Okay. So what's the maximum bending moment? Where it will be there? See, for a simply supported beam subjected to concentrated load at the center, say, what is the maximum, where the maximum bending moment will be, what is its value?
Sir, it's at the point where the force is applied, and it is.
What is the value, do you remember? P and L is this one, say.
Uh, Sir, I think PL by 4, if I'm not wrong.
PL by 4 only. It's very simple. You see P by 2, and then you multiply this one. So PL by 4 itself. So that is a maximum bending moment. Okay. So now where do you think the where yielding will start first here in this beam? Which is a critical point actually in the beam, where failure you will see. So this is a bending moment diagram. So this is a bending moment diagram. So where where you will see the plastification will start. Which point?
Sir, at the center itself.
So everything starts at the center. Okay, because so now here also as already we told at the center only. So when P, so this is our bending moment diagram. So when M is 0 here, anyway, everything will be 0. When M is equal to My, say, so these are our bending moment diagram. So the maximum bending moment will be at the center. So now at the cross section also, as already we explored, right? So it will not become suddenly, okay? So first elastic yield thing it will reach, then some portion will be plastic, some will be elastic. Then finally the whole thing becomes, the plastic hinge. So this is how it happens actually, okay? So M is equal to MP, and finally you see the plastic hinge forms here, and then slowly say the plastification, so this portion also has exceeded M of Y. So here also slowly the plastification happens, and this is what you see, we call this as a plastic hinge actually, okay? So this happens. Now what happens when hinge is formed? So once hinge is formed, say, what will happen to this beam? So it is like a simply supported beam, say. Already you are having hinges at the supports. Uh, Now here also you have a hinge actual. Now what happens to this beam? And then you are applying a load, whether it will be able to take this load. See what happens once a hinge is formed here, say. What happens to this beam? See what happens. Already here you are having a mechan that other hinge, but here you are having a plastic hinge actually. So now what happens? What type of failure it is, or what happens here? It will be able to take the load, or what happens exactly?
It collapses, sir.
It just how it is going to collapse, something like that. It becomes unstable. So right, for simply supported beam, that determinacy, stability you would have studied in your analysis course. So three hinges say automatically, it just collapses itself. So this is how it happens. So now at this collapse point, say. So anyway, because we are assuming everything linear, I already told you, right, in the stress strain curve or in the moment versus curvature. So we are going to neglect, this type of a thing. So now what this collapse say? So the bending moment will be MP. This is a plastic moment, or the moment at collapse. So this anyway is the maximum bending moment is a PL by 4. So this is your ultimate load, or the collapse load, say. So from this, if you equate, you can find out this collapse load. So if you know the plastic movement, say, so PP is equal to 4 MP by L itself. So this is how the collapse load happens actually. Okay. So this is a very easy for a simply supported beam, because it's a determinate and it is very straightforward. And since we have ignored these non-linearity, right? These all these complicated things, okay, like this portion. So these are non-linearity here, and then strain hardening, all those things. So it becomes just very simple kind of things itself. Okay, very easy to calculate. So that's what. So now this concept of plastic hinge, say, whatever we are saying, it is basically a physical approximation. Okay. So basically now, because this curve, what it shows is when you do like this, it shows that at MP, okay, the curvature is infinite. Okay. In reality, there is nothing called as infinite curvature. I already showed you the photographs itself, how the things will fail. So this is just a physical approximation. You will not see, the beam will not break into, you follow, right, two piece or whatever. The infinite things is not possible, and without complete fracture of the beam itself. So it's just a physical approximation. Okay, and then more correctly said, this high curvature basically occurs over a short length basically. Okay, on either side of the section of the maximum moment. So there is this portion basically. Okay. So now and upward, so this may so on the other side of the section is of the maximum moment, and by the increase of moment of resistance at this section to a value in excess of the plastic moment, thus enabling the plasticity to spread. So it spreads also, and then as already I told you, the strain hardening also is there, which we have ignored actually. So that also will happen, but we are ignoring all those issues itself. But generally, when you test it experimentally, say, so for mild steel, they say that this whatever plastic hinge concept, whatever we have discussed now, they say that it is a close approximation. It is not exact thing what happens. You will not see at the failure, but it's a very good approximation. To the truth, and it matches nicely. Not exact 100% with some error is there, but with the experimental results also. Now here also, so now suppose this is what we are calling as elastic perfectly plastic actually. Suppose if I have my stress strain curve or whatever, so if it is like this, what do you call this type of material? Just like this, no slope. So this is elastic perfectly plastic or whatever. So this is what we call. What do you call this type of stress? What do you call this type of material? Just it is a no deformation. Suddenly, it collapses. What do you call this one? What type of material is this one? It's no elastic thing. You followed here. There is no elasticity here. Suddenly it comes like this. This you call as? I have already written here. What is this one? What is this here? What type of material is this one? So what type of material is this one? Can you read?
Sir, a rigid plastic beam.
So rigid plastic beam means no deformation, sudden collapse actually. That's what we call as a rigid plastic beam. So, but generally our beam is elastic plastic only. But what we are assuming is the same simply supported beam say, okay, so AB, but when it is a failing basically. So what we are saying is this failure is like in a rigid plastic one. It's like a rigid link mechanism, we call this one. In reality, it is not possible, okay, because I already showed you these images, no, this figure in the starting. So it will not, it is not possible. I don't know where that figure. So it is not possible that it will collapse. So it will be like this. Okay. But anyway, so our assumption is, the failure thing, it happens like, so this is what we call as a rigid link, the mechanism itself. So this is what, how it, so hinge forms and suddenly, these are all like rigid elements like that, these are an assumption. We try to assume, something like this. So we ignore like, the plastic hinge, how much is the length of the plastic hinge and all those things we ignore. Once hinge forms say just it collapses like this, it becomes just into two pieces like a rigid link mechanism. So this is also assumption actually in our this one. So for a simply supported beam say the collapse load is 4 mp by L. It's very simple, we have done by making a lot of assumptions, linear and all those things. So you can easily calculate this collapse load. For determinate structures it is very easy, but if you have indeterminate structures say, it becomes very interesting. So it is indeterminate structure. And now can you tell me what is the indeterminacy here? Degree of indeterminacy for this propped cantilever. So what is the indeterminacy for this propped cantilever? Now, what's the indeterminacy? It's a propped cantilever. Now, what's the indeterminacy? You would have studied, right, in our analysis courses. Is a roller support here. What's the indeterminacy of this one? How many unknowns and how many equations are there?
Sir, 4 unknowns, 3 equations.
So what is the indeterminacy?
1.
One basically. Okay, so this is how, and how do you solve this? Right, all these things. How to solve indeterminate structure? You remove the redundant thing, you superimpose, you calculate both the cases and then you superimpose. So the bending moment diagram say for this case will be something like this. You followed. So something like this, the bending moment diagram will be. Of course, this is at the load. Okay, so you will see something like this is a bending moment diagram. And where will be the maximum bending moment? I have written the numbers also here. For a concentrated load, the maximum bending moment is at what place, and the load is also exactly at the center. See these numbers and tell me. So here it is 3 PL by 16. That is at the fixed support, and below the load side is a 5 PL by 32. Where it is maximum for a propped cantilever. See where it is maximum. See the numbers also provided you. So where it is maximum for this bending moment, where it will be maximum. You can see the numbers here.
At A.
At A. So at the fixed end only, you will have the maximum bending moment. So now let us say for this problem, interesting. So let us take EI is a 10 kilonewton per meter square. And let us say for this problem from experiments, say people have tested, they have found out that the yield moment is 7.5. So when the bending moment reaches 7.0 less than 7.5, that means the whole beam is under the elastic stage. And if it exceeds 7.5, it's elastoplastic. And the plastic movement, that is a collapse kind of thing, is 9 kilonewton per meter. Okay, so these are the things which has come from the experiments. Okay, and let us say span is 1 meter. So this also we take, and then let us do what happens, how this beam is going to collapse actually. Okay. And now let us say the load is a 32 kilonewtons. Okay, very small, 32 kilonewton is the load. So now when the load is a 32, say, you substitute here in these expressions, you know you how to calculate in your structure analysis. So 3 PL by 16, say, substitute. So this is a bending moment at A, and this is a bending moment at C, 6 and 5 actually. So what is your comment? Our yield moment was? So the yielding to start, so yield moment is 7.5. So what is your comment here? The beam is safe, or what, in which stage beam is? So in the beam, say, where is your beam basically? So the bending moments are less than the yield moment, that is 7.5. So that means your beam is in which stage? Which stage beam is in? The bending moments are lower than 7.5. That means your beam is in. So to start yielding, the bending moment has to reach 7.5. Okay, but the bending moments are 6 and 5 only, less than this one. So that means your beam is in which stage? Here or here in this curve? See, all of you are there. So which stage the beam is in? All of you, yes, yes. So the beam is in which stage? 7.5 for this 32 kilonewton load, say. So it is where it is. The beam is in. So 6 and 5 actual. So which means the bending moments have not even reached the 7.5. So that means your beam is in elastic stage only. You followed. So there is no failure in the beam or whatever, and you can even calculate the deflection. So anyway, the deflection, the maximum deflection will be below the load, and this formula also from your structure analysis, WLQ, the PLQ by 768 EI. So this is the deflection factor, 29.17 mm. And of course, this is a fixed end say. So here the rotation is zero actually, okay, because it is a fixed end itself, okay. And now we increase the load to 40 kilonewtons actually. So now when the load is increased to 40 kilonewtons, and once again you calculate MA and MC, okay, that is the same formulas you use, say, that is 3 PL by 16, so 3 PL by 16, and then 5 PL by 32, or whatever you use the same formulas. Now what's the bending moment at A? So the bending moment at A is 7.5 we have got actual. Now at C is 6.25. So now what does it tells you? What is your observation now? And yield moment is 7.5. So what is your observation now? What is observation? See, all of you are there. You are able to hear.
Yes, sir.
So what is observation now? See, now load is 40. At A, now the bending moment is 7.5. At C, bending moment is 6.25. Other places anyway less than this one only. Now your yield moment is 7.5. So what will happen? So what will happen? So at A, say, if you try to compute at A, the stresses actual, okay. So what happens? The top fiber and the bottom fiber, say, they will reach, the yield stress actually. You followed. The yielding has already started. And now this is a deflection. You can calculate for this load. The same expression is valid. 40 if you substitute, say, 36.45. And rotation at A is still zero actually, okay. So this is what it happens. Now, when you increase the load to 48 kilonewtons, okay, and then once again you calculate MA and then MC, say. And now what is the bending moment at A? What is the value? If you substitute here, so what is your observation? So now what is your comment at A? At A, what has happened? See what has happened. Are you able to follow what I'm talking? So the bending moment at this place is 7.5 and the bending moment at this place is 9. So what is your observation? And the plastic movement, as already I told you, MP is 9 basically. Okay. So what does it tells you? At A, what has happened? See, all of you are there. See what has happened.
Plastic stayed open.
Now, plastic, this one has happened basically. Okay, so what has happened is, so this place, the hinge has formed. Actually, the plastic hinge has formed. And if we calculate deflection, say same formula, if you use 43.75, this one. But now, what C say? Now, what will happen here? Now if you add some more loads, what will happen? So now this hinge has formed here. So now your propped cantilever has become like this. Okay. So this is our roll. This is this side, and here you are having a hinge basically. Now what will happen? Now if I increase the load, say, what will happen to this place? The beam will collapse or it will still stay this one. So hinge has formed at the fixed end. Now what will happen? So the beam is a collapse or what will happen? Now what will happen to our this one? So now this is our propped end. Now hinge has formed actually. But at point C, still the bending moment is, the maximum bending moment is 7.5 only. Here it is 9 kilonewton. So that means, here hinge has formed basically. Okay. And now what is your comment? So now if I increase the load, say, now what will happen? The beam will collapse or still it will take some more load? Yeah, come on, tell me, So this you have studied, right, in analysis also. Now what will happen? See, at A hinge has formed. At C, it is still 7.5 kilonewtons only. Okay, it has only reached the yield one. So 7.5 means only the top and bottom fiber only are in the yield. To make the whole section plastics, you require 9 kilonewtons basically. Okay, now what will happen? Now tell me, what will happen now? Okay, you are putting in the chat box. It can take some more load, but how it will take some more load? What will happen? Which place will take this load? This will get transferred to which place? So now in our plastic analysis, I already told you in the assumption that is, once a certain place is a plastic, it has been plastified, say. Now that place will not take any more load at all. Okay, the whole load will be taken by the remaining portion of the beam itself. Okay, so that's what the main our assumption itself. Okay, so now what happens is, because it has a plastified, say, still it can take some more load, but now because it has become like a hinge, so this entire beam, say, so this A point A will not be able to take any more bending moment. Okay, so the whole propped cantilever becomes like a simply supported beam. Okay, so here also you have this one, here also you have this one, and this is our load. Now let us say we have increased the load to 54 kilonewtons basically. So that means the extra, that is 6 kilonewtons, we have increased the load here from 48 to 54. So now this extra load, say, whatever is there here, so now this portion, the fixed end, the already plastic hinge has formed. So your propped cantilever has become like a simply supported beam only. So this additional loads will not be taken care by your fixed support. The remaining portion of the beam only has to take. So now when you take 54, say, now what happens is, anyway this has plastified. Okay, so it cannot take any movement. It will is 9 only. But previously it was 7.5 here. So this extra loads will be taken care by this portion of the beam actually. Okay, the other remaining portion, and then you will see this this portion. So here also the bending moment has come to 9 kilonewton per meter. Okay, so now what has happened is, here also hinge has formed. Now here also hinge has formed actually. Now what will happen to this beam? Two hinges have formed means. Yeah, so here also you have a hinge. Here also you have a hinge action, and if you increase the load some more, so what will happen? Now what will happen? It will take any additional load beyond 54, or what will, it will collapse, or what will happen to this one? Now it will take any more load, extra load. So one hinge has formed at A, still it was taking load. Now another hinge also has formed at middle also. Now what will happen? Yeah, what will happen now? Whether it will take any more load?
No, sir.
Yeah. So finally, what happens? It collapses because two hinges have formed. So it is like a simply supported beam. So propped cantilever to simply supported, and then simply supported only one hinge at the center. Obviously, just now we have said you followed it. It just collapses like this. Okay. So this is how this is what we call as a mechanism or a beam mechanisms, and it will lead to collapse itself. Okay. So these are the deflections and rotations you can calculate. So anyway, time is done. So we will continue in our next class. Okay. So if there are any questions, you can ask.